We measure heat or energy in units of calories or joules. Now, if you're thinking calories like food calories, you're absolutely right. But you notice here that calories is in a lowercase c, whereas if you look at a nutrition label, calories are actually a capital C calories. And sometimes if you actually go outside of the US, some of those nutrition labels will actually say kilocalories. And that's exactly what it is. A food calorie is a kilocalorie. So you can think of it as 1,000 calories is equal to 1 food calorie. Joules, same thing. Sometimes you might see kilojoules. So 1,000 joules is equal to 1 kilojoule. So when there is a temperature change, we're going to use the formula Q equals MCAT. If you don't remember what this formula is, Q stands for heat or energy that's absorbed or released. M stands for mass in grams. C is the specific heat value, which is given to you almost always. And triangle T is delta T, meaning change in temperature, final temperature minus the initial temperature. Now, when the temperature does not change, and so we're talking about a phase change. Remember, the phase change is melting, vaporization, condensation, or freezing. During those points of the heating curve, we're going to use the molar heat of fusion or the molar heat of vaporization. And in that case, you're going to use the formula Q equals moles times molar heat of fusion, or Q equals moles times molar heat of vaporization. So notice that for this one, I'm talking about moles and not mass, right? So if you're given mass, we're going to go ahead and convert that to moles, which you'll see later on. So the first example, before I even get to the example, I want to point out these two tables here. So on the right side is the specific heat capacity of 4 different metals, okay? And then on the left side, we have molar heat of vaporization, molar heat of fusion of water, ethanol, methanol. So I gave it to you like this just so that you can see that basically all the substances have their own unique specific heat capacities or heat of vaporization and fusion, but we're also going to just practice trying to figure out which one of these we're going to use. So example 1 says, how much heat is absorbed when 42.0 grams of gold goes from 25 degrees Celsius to 35 degrees Celsius? Well, the first question is there a temperature change? And the reason why I asked that is because we talked about 2 different formulas just now, right? We talked about Q equals MCAT when there is a temperature change, and then we talked about Q equals moles times heat of fusion or moles times heat of vaporization when there is no temperature change. So asking that question first will give you the direct path, basically, for the rest of the problem. So here we see that there is a temperature change. It goes from 25 degrees to 35 degrees Celsius. So we are going to use the formula Q equals MCAT. The next question should be, well, which one of these values are we going to use? Well, it's of gold, and we want the specific heat capacity, not the vaporization or fusion, because remember there is a temperature change. So we're going to look at gold, 129 joules per kilogram degree Celsius. So let's go ahead and plug in those numbers and solve. Mass, we have 42 grams. C is specific heat, 129. Delta T is temperature change, final minus initial, 35 minus 25. So we want to first see if our units will cancel each other out, right? So if we look here, and think algebra, right? So if we look here, you know that we're going to multiply all the numbers at the end. So if we multiply all the numbers, we want to, again, make sure that it's going to multiply nicely, right? And that our units will cancel out. So here we have grams and kilograms, and they won't cancel out, right? So what are we going to do? Well, we want to then convert the mass, okay? We want to convert it to kilograms. So that's going to be simple. 42 grams, set it up as the fence. Grams will go on the bottom, and there's 1,000 grams in 1 kilogram, so we're going to put those numbers in there. And that's 0.0420 kilograms. So let's go ahead and rewrite our problem with the new number. So we have 0.0420 kilograms. Nothing else changes. Let's go ahead and subtract the temperatures. That's 10 degrees. And then we're going to go ahead and make sure all our units will cancel out. Kilograms cancels out. Celsius cancels out, which is nice because then what's left over? is joules, right? So we're going to multiply 0.0420 times 129 times 10, and we get 54.2 joules. Example number 2. How much energy is given off when 3.2 moles of steam condenses to liquid water at 100 degrees? Now, again, the first question is there a temperature change? No. In fact, it says that it is at 100 degrees Celsius. There's a couple key words, though. Condenses, right? At 100 degrees Celsius. So if we take it back to the heating curve, what section am I talking about? I'm talking about the part where the substance is condensing, right? In between D and E. So that we talked about earlier, we'll be looking at the molar heat of vaporization. Okay, so if we look at our chart, and this is of water, right? It says water at 100 degrees Celsius. We're focusing on water here. And we're looking at the heat of vaporization. So everything else we're gonna go ahead and ignore. Okay? So we're gonna now set up our formula as Q equals moles times molar heat of vaporization because there is no temperature change. So this one is nice. We're just going to plug it in and solve. 3.2 moles times 40.7 kilojoules per mole. Our moles will cancel out, and we get 130.24 kilojoules of energy. If we're thinking about significant digits, we only want 2 significant digits here, so we have 130 kilojoules. Example number 3, calculate the heat required to melt 125 grams of ice at its melting point. Now again, the first question is there a temperature change? No, in fact, no temperature is listed. It just says melting point, right? But it's talking about ice at its melting point. We should know this by now. Water's melting point is 0 degrees Celsius, right? And so if we're taking it, again, referring back to the heating curve, we're talking about section BC, okay? And there, we would be looking at the molar heat of fusion. So if we look up here, we're focusing on water's molar heat of fusion, okay? And we're going to set up with the formula Q equals moles times molar heat of fusion. Now, the formula is moles, right? But what are we given? We're given grams. So what are we going to do? That's right, we're going to go ahead and convert. Now this is a simple conversion where we're just going from grams to moles. So bring down grams of water. We're going to convert it to moles of water. Molar mass of water is 18.02 grams, right? So 18.02 grams of water per 1 mole of water is equal to 6.94 moles, okay? So we're going to use that number, 6.94 moles, and we're going to set it up. 6.94 moles times 6.01 kilojoules per mole, and we get 41.7 kilojoules. Now you try. Example number 4 and example number 5. Example number 4 says calculate the mass of copper in kilograms when heated from 30 to 150 and releases 12,500 joules of energy. So we'll go ahead and pause the video here, try it out yourself. Okay, remember the first question is there a temperature change? All right, because there is a temperature change, we are going to use the formula Q equals MCAT. We're going to look at the specific heat capacity of copper, which is highlighted in red. And the difference here is that I'm asking you to find mass. So what is 12,500 joules? That's your Q, right? So Q is equal to, or 12,500 joules is equal to X times 387 times 150 minus 30, and you get 0.27 kilograms, okay? So again, if I write this out here, we have 1, I'm doing this with my mouse, so I apologize. That's going to be messy. 12,500 joules is equal to X times 387, and the change in temperature, 150 minus 30. So I hope you were able to set it up like that. and solve for x, 0.27 kilograms. Okay? All right. Last example, calculate the heat required to vaporize 31.8 grams of methanol at its boiling point. Again, first question is there a temperature change? No, right? And it's talking about vaporizing and at its boiling point. So what are we talking about? What do you need to know or use? The molar heat of vaporization, right? And this is of methanol, so make sure that you are looking at methanol and nothing else. Go ahead and pause the video here and set it up and solve. And you should have gotten an answer of 34.9 kilojoules. If you did not, maybe you forgot to convert your grams to moles. Okay, so make sure you do that, right? The formula is given here for methanol. You had to look on your periodic table for that. All right, so if you do that again, you'll get 34.9 kilojoules. And that's it for thermochemistry.